Hello viewers, we will introduce the important theorem, that is Leibniz theorem for differentiation under the integral sign. Here we see that the lower limit is a function of x and the upper limit also a function of x. That times we differentiate with respect to x. Here integrand is f of x comma. So two variables, but f of x comma b of x is a function of one, that's our one variable, and there are two variables. That's interesting relation between the two parts. We'll prove that's there. So first time we use what's f of x. F of x comma t be the continuous function, and del f by del x be also continuous in a domain. That's a domain in x, that's domain in xt plane, and this domain is defined by the two interval x naught less than equal x and less than equal x1, and the another interval a of x less than equal t and less than equal of x. These two interval makes a rectangle in xt plane. So f of x comma t and del f by del x be continuous in the rectangle, where a x and b of x is continuous and derivatives in this interval. So satisfying this interval or condition, the Leibniz theorem is in here. So let's go. F of x comma t equal to del t f of x comma. The above relation is denoted by another format, that means 0 0 x comma t. That means no derivatives with respect to x or and f of 0 comma 1 x comma t. It represents this function is derivatives with respect to t only. So it represents the partial derivatives with respect to t. So it can easy to say f of 1 comma 0 what represent it. This is also a partial derivatives with respect to x. So also write the previous relation f of 0 0 x comma t equal to f of 0 comma 1 x comma t. Integrating both sides with respect to t, then we get ax b of x f of 0 comma 0 xt dt are the integrating variable, that equal to f of 0 comma 0, because this represent the partial derivatives with respect to t. So when we integrate with respect to t, then it can be written 0 0. So it means that no derivatives with respect to x or and the lower limit, and this is the upper limit. Putting these values, and we get f of 0 comma 0 and x comma bx minus f of 0 comma 0 and x comma ax. That's the easy term. Now differentiating the both sides with respect to x, then we can write ddx and a of x, b of x, a 0 0, that's gives respect to x, and here are integral. So when we derivatives this term with respect to x, then first time we derivatives this term, that's the partial derivatives, and the next terms would be partial derivatives with respect to x, then the derivatives so with respect to b of x. So this can be written as f of 1 comma 0, so with respect to x derivatives there are a variable, and that time must be derivatives with respect to x, this term only x, and next term f of 0 comma 1, that means this function is derivatives with respect to b of x, that means x comma b of x. So we derivative b of x with respect to, and similar for this function, so we can write f of 1 comma 0, and there are x a of x minus so there is another term dxx, and minus f of 0 comma 1, x comma a of x, and d a of x divided x. So f of 0 0, that means no derivatives of capital of x. When we differentiate with respect to x, then the partial derivatives 1 comma 0, that means the partial derivative with respect to x, and the second times the partial derivative with respect to b of x, that means 0 comma 1, and the derivatives of bx with respect to x, and similar to derivatives of x with respect to x, and the similar for the second terms. So we find the four terms. Now we'll explain these four terms. ddx of x, that is 1. So it is very easy term, and similar this. We can write this term in easy format. That means it is a function of partial derivatives with respect to b of x. So we can write it. That means this represent a same as this. If we write there are b of x and b of x, and this is the same case, so we can write it f of 0 0 and x comma b of x, and similar for this function. This function also can be written as if it is a of x and it is a of x, then it can be written as f 0 0 and x comma a of x. That is a very easy term. We explain these terms, and so these two terms can be written easily, and the another two terms we can explain the another two terms in another slide. So let's go please. So ddx of integrating a of x and v of x f 0 0 x comma t dt equal to f capital F of 1 comma 0 and x b of x plus or minus f of m. Last terms will be rearranged, then f of 1 comma 0 and there are x comma ax, so this represent the partial derivative with respect to x and this represent also same, so we can write in same f of 0 0 and x b of x and the derivatives with respect to x, the second term will can be written as this form and the last terms that can be written f of x comma a of x ddx of ax. So now we will see that the first two terms what would be written in. So let's go please. The first two terms, for this reason we write the previous finding, that means a of x and b of x f of 0 0 x comma t dt equal to f of 0 0 x comma bx x comma b of x minus f 0 0 and x comma a of x. Now we'll replace 0 by 1, that means this means 1 comma 0 means the function f is derivatives, partially derivatives must be with respect to x. So this is 1, this means the partial derivatives of a with respect to x, so this can be changed. So these two terms is similar, these two terms, so interchange these two terms with this only single, and these terms what reference, if we write this in a del x, so we can erase this, so del f x comma t, so this term can be replaced for these two terms, first two terms. So let's go right, equal to a of x b of x del f of x comma t dt plus f of x comma bx, we cannot write 0 0, that means 0 0 means no derivative, so this means no derivatives, and that dx ddx of vx and minus f of x comma a of x and the ddx of a of x. So it is the proof of Leibnitz theorem for differentiation under the integral sign. Thank you very much.